Ladies and gentlemen, my name is Jiaqi from Zhejiang University in China. I'm glad to have the opportunity to make this presentation. The topic of my presentation today is suppression of Rayleigh-Taylor instability in a gas-liquid standing wave thermal combustion engine. My supervisor is Professor Tao Jin. My presentation today includes 4 sections. Firstly, I would like to introduce the background of the research. Low-grade heat from natural sources and waste heat from industrial processes is abundantly available but not yet effectively used due to its low temperature related to ambient environment. Statistical analysis reveals that 72% of the global primary energy consumption is lost after conversion, among which the biggest share of 63% arise at a temperature below 100 centigrade. Therefore, utilization of low-grade heat can improve the energy efficiency, thereby relieving global energy demands and reducing greenhouse gas emissions. Recently, thermal combustion engine has attracted much interest thanks to its outstanding features of high reliability and environmental benignity. Based on thermal combustion effects to realize the conversion between thermal energy and mechanical energy, thermal combustion engines can be applied for refrigeration, power generation, gas suppression, and so on. In thermal combustion engines, onset temperature difference and damping temperature difference are critical parameters for the application of thermal combustion engines to recover low-grade heat, where onset temperature difference is the lowest temperature difference to trigger thermal combustion oscillation, and the damping temperature difference is the lowest temperature difference to maintain thermal combustion oscillation. Therefore, many efforts have been devoted to decrease onset and damping temperature difference. One of the effective methods is the introduction of liquid column into a gas-only thermal combustion engine, and a series of numerical and experimental studies on gas-liquid thermal combustion engines have been conducted. Various effects, such as liquid and working gas, on onset temperature difference are analyzed. In 2017, Rayleigh studied the effect of liquid column on the specific acoustic impedance and phasing difference between pressure and velocity in the regenerator, and found that the liquid column can increase the specific acoustic impedance while keeping the traveling wave phasings in the regenerator to achieve a low onset temperature difference. The Rayleigh-Taylor instability is induced when a light fluid accelerates a heavy fluid. Since the oscillation of working gas can accelerate the liquid column in half of the cycle, the instability can occur in a gas-liquid thermal combustion engine. MITAB employed 2 methods to suppress the instability in a gas-liquid traveling wave thermal combustion engine. The first method is the enlargement of tube cross-sectional area, and the other one is the installation of a submerged float. Their experimental result shows that this method can successfully suppress the instability and increase the pressure amplitude by almost twice. Besides, they found that the onset temperature difference hardly changed after suppressing the Rayleigh-Taylor instability. However, in this work, we found that whether the instability is suppressed or not can have a great effect on onset temperature difference of a gas-liquid standing wave thermal combustion engine, unlike MITAB's results on a gas-liquid traveling wave thermal combustion engine. Now, we move to the section 2, experimental system. The gas-liquid standing wave thermal combustion engine employs a symmetrical configuration. The engine is composed of 2 sets of hot buffer, taper tube, hot tube, heater, stack, cooler, and a U-shaped tube containing liquid column. The heat transfer blocks inside the heater and the cooler are both of fin type and made of copper. The stack is composed of a number of stainless steel slides. The dimensions of main components are listed in the following table. In the engine, nitrogen of 1 million parts is selected as the working gas, and water is chosen as the liquid column. To suppress the Rayleigh-Taylor instability, a float is installed at each side of the liquid column. 3 Chino K-type thermocouples are employed to measure the temperatures of heater and cooler, where 2 thermocouples are separately installed at the top and bottom of the heater, and another one is installed at the cooler. The average of T1, T2, T3, and T4 is regarded as the hot temperature, and the average of T5 and T6 is regarded as the cold temperature. The temperatures of the 2 heaters are controlled to be the same by changing the electric power inputs, which is measured by Weibo PF 1200. A G-Unique 5000 pressure sensor is installed at each cooler to measure the pressure signal. The measurement error contains the systematic error and the random error. Based on the calculation, the measured errors of temperature and the resonance frequency are listed as follows. To measure the onset and the damping temperature difference, the experimental procedure on onset and damping processes is introduced. During the onset process, the input power to the heater is controlled to maintain the temperature elevation speed at the heater lower than 0.5 Kelvin per minute. At the beginning, the pressure amplitude maintains around 0 with the increase of hot-cold temperature difference. When the hot-cold temperature difference exceeds 82 Kelvin, the pressure amplitude experiences a sudden rise, indicating the occurrence of onset. Thus, 82 Kelvin is regarded as the onset temperature difference for the illustrated case. After a period of time, when the pressure amplitude tends to stabilize, the input power is turned off, and the damping process begins. When the hot-cold temperature difference drops to 51 Kelvin, the oscillation completely vanishes, and 51 Kelvin is considered as the damping temperature difference. We can see that the damping temperature difference is lower than the onset temperature difference, and the hysteretic loop is observed during the onset and damping processes. Similar phenomenon has also been detected in other types of thermal combustion engine. The third section is results and discussion. To suppress the Rayleigh-Taylor instability, cylindrical flows with different diameters and different lengths, and spherical flows with different diameters are employed. The corresponding dimensions are listed in the following table. Limited by the diameter of the U-shaped tube, the maximum flow diameter is 55 mm. The float is made of polyethylene, and its density is around 950 kg per cubic meter. Since the density is close to that of water, the float can follow the oscillation of water. This slide shows the experimental results using cylindrical floats with different diameters. The left figure presents the variation of onset temperature difference, damping temperature difference, onset resonance frequency with the diameter of cylindrical float, where the length of cylindrical float is fixed at 50 mm. According to the video from Multi, cylindrical floats with larger diameter are preferable to suppress the Rayleigh-Taylor instability. Therefore, with the increase of the diameter, onset and the damping temperature difference decrease. Using the floats with different diameters, the maximum difference in onset and the damping temperature difference are 21 Kelvin and 3 Kelvin respectively. Therefore, the diameters of cylindrical float can affect onset and the damping temperature difference, especially the onset temperature difference. Besides, both the lowest onset and the damping temperature difference is obtained at a diameter of 55 mm. indicating that an increase in the diameter helps to reduce onset and damping temperature difference. The onset resonance frequencies decrease with the increase of diameter, which can be due to the decrease of mean pressure with the decrease of onset temperature difference. The figure presents the effect of the length of cylindrical float, where the diameter is set at 55 mm. Based on the video from MITAB, cylindrical floats with longer lengths are preferable to suppress the Rayleigh-Taylor instability. Therefore, onset and damping temperature difference decrease when the length increases from 10 million to 30 million. However, when the length increases from 50 million to 70 million, onset and damping temperature difference increase instead, which can be due to the rise in friction losses between floats and the tube wall. The maximum difference in onset and the damping temperature difference are 24 Kelvin and 15 Kelvin respectively, indicating that the length of cylindrical float can have a marked effect on onset and the damping temperature difference. The lowest onset temperature difference is obtained at the length of 30 mm, and the lowest damping temperature difference is obtained at the length of 50 mm. Therefore, there exists an optimal length for cylindrical floats to obtain the lowest onset and the damping temperature difference. In addition to cylindrical floats, spherical floats are also employed to suppress the instability of the free liquid surface. 5 spherical floats with different diameters are used. As the diameters increase, onset temperature difference and the onset resonance frequency experience a decrease at first and then an increase, while the damping temperature difference experiences an inverse trend. Using the floats with different diameters, the maximum difference in onset and the damping temperature difference are 14 Kelvin and 7 Kelvin respectively. The lowest onset temperature difference is obtained at a diameter of 45 mm, and the lowest damping temperature difference is obtained at a diameter of 55 mm. Therefore, there exists an optimal diameter for spherical floats to obtain the lowest onset and the damping temperature difference. Comparisons between results with and without floats are conducted. The figure displays the relative deviations of onset temperature difference and the damping temperature difference obtained from the conditions with floats to those obtained from the condition without floats. It is found that the installation of float is not always beneficial to decrease onset temperature difference and the damping temperature difference. Besides, the decrease in onset temperature difference does not mean the decrease in damping temperature difference, and vice versa. Therefore, suitably sized cylindrical or spherical floats should be used to decrease onset and damping temperature difference. With the exception of the floats A, D, and F, both onset and the damping temperature difference are decreased after installing floats. As for cylindrical floats, the maximum decrease in onset temperature difference is 19% using the float E, and the maximum decrease in damping temperature difference is 21.8% using the float C. As for the spherical floats, the maximum decrease in onset temperature difference is 18.6% using the float I, and the maximum decrease in damping temperature difference is 13.1% using the float K. Compared to the spherical float, cylindrical floats can obtain lower onset and the damping temperature difference, especially the damping temperature difference. Finally, some conclusions of the presented work are made. This work used floats to suppress the Rayleigh-Taylor instability in a gas-liquid standing wave thermal combustion engine. based on which the effect of the instability on onset and the damping temperature difference are analyzed. Some conclusions are as follows. Firstly, the installation of suitably sized flows can reduce onset and damping temperature difference. Compared to the conditions without flows, the maximum decrease in onset and the damping temperature difference are 19% and 21.8% respectively. Secondly, the dimensions of flows have a marked effect on onset and the damping temperature difference, and there exists an optimal dimension for cylindrical and spherical flows to obtain the lowest onset and damping temperature difference. Thirdly, cylindrical flows can obtain lower onset and damping temperature difference than spherical flows, especially the damping temperature difference. That's all for my presentation. If you have any question, please feel free to contact me. Here is my email address. Thank you very much for your attention.